First of all, I'm thrilled to be here. Thanks so much to Thomas and to Elio for organizing this wonderful conference. It's my first time in Stuttgart. I love your public transportation and your vineyards, okay? It's great. I always thought about Stuttgart as, you know, a car place, and I didn't appreciate how beautiful it is. So thank you very much, and I could ride your trains all day. And for €9, maybe I will. Anyway, and thank all of you for staying to the end. As you know, Piers and I had trouble reaching escape velocity from London, and so unfortunately we only arrived halfway through the conference, and I apologize to those of you for whom we missed it, but please blame Eurowings. All right, so today right now I'd like to tell you about my adventures with Pavel Volkov at Rutgers and Piers, who's here, on superconductivity in dilute quantum critical polar metals. So as you'll see, it's unconventional in some ways and conventional in others, and that's what gives us some fun. And it's a very old problem. Okay? So for those of you who are students, some things that are old are still interesting. We like to believe that. All right, so what is the challenge here? We have isotropic superconducting pairing without retardation. How do we overcome Coulomb repulsion? Okay. And what our merry gang is going to propose is that we have interactions between electrons mediated by energy fluctuations of the polar medium. But let's start at the very beginning. Okay. What is a polar metal? You think of a polar system as, you know, a system with a dipole moment. Well, what do you mean by polar metal? Why don't you get screening? Well, some time ago, last millennium, in fact, Anderson and Blount at Bell Labs suggested that if you had a polar insulator and doped it, okay, and at this point, this was a very abstract suggestion, you could have an inversion symmetry breaking transition with a polar axis, even though you don't have a macroscopic polarization. So this was suggested in 1965, and it lay dormant for a very long time. But more recently, people have actually made these things. They've made them intrinsically, for example, by doping for electrics, but they've also engineering, but also intrinsically. And in particular, in the search for vital semimetals, there have been a number of polar semimetals that have been found. And the polar transition can be tuned by chemical substitution, by strain, and by pressure. And in fact, as you see, it can be tuned to 0. So as we heard in Lucas's talk, and many talks, I believe, throughout the workshop, particularly on Monday, when we have a quantum critical point, the natural question is, can we get exotic phases? Okay. So the first thing we can ask is, can metals near polar quantum critical points host strongly correlated phases? Because after all, one of the reasons that people are interested in quantum criticality is to get novel phases, novel metallic phases, and of course, exotic forms of superconductivity. And we know very well that the form of the novelty is dependent on the details of the quantum critical point. So can we get this near polar quantum critical points? And the challenge here is, how do you get strong coupling of the electron to the critical Q = 0 polar mode? Remember, the critical boson here is a transverse optical phonon that breaks inversion symmetry. So our standard coupling, the Yukawa coupling, where you're coupling the electron density to the critical mode, doesn't work on symmetry grounds. Okay, if we don't break time reversal invariance, okay, if we don't have spin orbit coupling, and we'll be talking about that shortly. Okay, the question we can ask is, can we construct a fermion bilinear that breaks time reversal, that breaks parity but doesn't break time reversal, it turns out that in a single band without spin-over coupling, you can't do that. So you have to go to multi-band, or you have to introduce spin-orbit coupling, both of which, of course, have been done. So one of the things that Pavel and I looked at was we said, let's introduce multi-band. But then, of course, you'll get the strongest coupling when you're at band crossings. And so we investigated 3 distinct band crossings, a 3D nodal line, a 2D Dirac points, and then 3D Weil points. And this is with time reversal breaking. This was just to reproduce prior results to make sure we knew what we were doing. And indeed, in this particular case, we actually got the Gross-Neveu model. That's how I knew that the Gross-Neveu model has non-Fermi liquid behavior. And because of the polar axis in these materials, you get some interesting experimental results. You get phonon anisotropy, you get all kinds of things. And we've been talking to our density functional theory colleagues to try and identify materials where we might have this. Part of the problem is you need to have the Fermi level pinned to the band crossing. Okay. All right. So we've done that, but now the question I'd like to address today is, can polar criticality drive dilute superconductivity? That's going to be the question we're going to address. Now, the poster child for dilute quantum critical polar metals is strontium titanate. This is a very old problem, as we'll discuss in a minute. And I won't be able to put all the references because, as you'll see, it goes back to the 60s. So I'm going to rely heavily on nice reviews from my colleagues. This is a nice review by Kamra Benia and his collaborators, which reviews the experimental situation there. So here we have Tc as a function of n. We have dome in Tc, okay? And we also have, at lower densities, another dome. This tends to be filamentary, so we're going to focus on this. Now, what's the issue here? Well, the issue is that it's a very low density. When you have an insulator, okay, and you want to dope it, Maud told us that basically, if in 3D, the density to the 1/3 times the Bohr radius is a constant. I think he found it was a third, something like that. Let's say of order 1. Now, the point is that the Bohr radius in these systems is rather large, and that's because the dielectric constant is large. So if you dope an insulator, you become metallic at very, very low densities. Okay, now this poses a problem for superconductivity because typical Fermi energies are in the order of 10 Kelvin, okay? But typical Debye energies are in the order of 400, 500 Kelvin. So the point is that TF is significantly lower than the Debye energy. And you may remember that for BCS, you count on having a distinction of energy scales where the electronic energy scale is significantly higher than the phonon energy scale. You want to have fast electrons and slow phonons. And here we have the exact opposite situation. We have slow electrons and fast phonons, and that's due to the diluteness, okay? However, even though we have the energy scales switched, a little bit of a teaser in all of this is that 2 gap over Tc is a BCS kind of value. So there's something about BCS that remains, but, okay, we have slow energies and fast phonons. And please recall, and this is specifically to the students in the audience and young researchers, of which we are all young, of course, the key point here is that normally when you have fast electrons and slow phonons, that's how you can use retardation to get around the Coulomb repulsion. But now the question is, what do we do? Because remember, the electrons don't like each other, okay? And we've got to get them to interact. And one suggestion that came very early on in this game by Larkin, Gurvich, and Firzov was that maybe maybe we could couple to a longitudinal phonon. But the problem is that even if we focus on this region of the densities. We are not going to talk about this because our experimental colleagues tell us that we have bulk superconductivity that is filamentary, so we're only going to focus on the higher dome. Even in the slightly higher densities, the point is that our Fermi energy is less than our optical phonon. So we don't have any phonons to help us, and yet we have this BCS value. So what do? Okay, so let's just remind ourselves a little bit about the history. Okay, we heard this morning from Leah about predicted superconductors. Strontium titanate, superconductivity in strontium titanate was actually predicted by Marvin Cohen, but it was predicted in a pretty funny way. Marvin Cohen, just after, you may remember, BCS came out in the late 50s. It was one of the aspects that was very surprising was that metals, poor metals made good superconductors and good metals made bad superconductors. So Marvin Cohen, who is an expert in semiconductors, said, look, we understand semiconductors really well. They are bad metals. Let's think about superconductivity in these systems because we really understand the normal states in semiconductors. So of course, he was an expert on gallium arsenide and germanium and all of this. The band structure of those was known very well, particularly gallium arsenide, which is multi-valley. He had read the Russian paper, which said that in polar semiconductors, it would be hard to get at low densities superconductivity because of the fact that all the Fermi energy was low. But what Marvin Cohen said is the following. He said, look, we have to get around Coulomb repulsion, which is the long wavelength phenomena, okay? A Q equals 0 phenomena. But what if we had a semiconductor that had many valleys, okay? Then what we could do is we could have multi-valley large K vector superconductivity that would get around Coulomb repulsion. The band structure of STO was not known at that time. So Marvin Cohen came up with a theory, and he went to he was at Berkeley at the time, he went to his colleagues, experimental colleagues, he predicted a TC as a function of n density, and oops, I think I've skipped one. Okay, I'll go back to this. I'm going to tell you about this in a minute. I went one slide ahead. Okay, so this is what Marvin Cohen did. And look at this theory and experiment. TC as function of n, that's experiment. This is the theory. All right, a slight wrinkle in the mix. When Len Mathis at Bell Labs did the band structure, STO still has only one valley. It's not multi-valley. So he predicted beautifully, look at TC versus experiment N, he predicted beautifully an experimental phenomena on a theory whose main assumption was wrong. He even got the Buckley Prize for this, okay? So he predicted it, the experimentalists saw it, we still don't understand it. I mean, Marvin Cohen admits to that. So that's our story with this. I skipped a slide, so let me just tell you, I'll go back to that in a minute. Well, why don't I go through the history and then sorry. I was spending so much time thinking about my story that I forgot what my order was. We went through this. Let me tell you the challenges and I'll go back to the history. So what are the challenges that we have in this system? We have how to overcome Coulomb repulsion. We have no retardation. And it looks like we have isotropic S-wave superconductivity. Okay. Normally, the way we can get around retardation is, for example, by playing with angular momentum. Here we don't have that. Okay, so how do we get around that? The other thing, which is very interesting, is that experimentally TC increases with the proximity to the polar quantum critical point. We were just talking a minute ago about the fact that it's very difficult to couple the critical boson, the critical polar mode, to the electron density. And yet, and these are some beautiful experiments by the Cambridge group, by Gil Lonswich's group, that if you look at TC as a function of pressure and approach the quantum critical point, TC definitely goes up. Okay, so the critical mode is a transverse optical phonon, but we have negligible direct coupling between the electrons and a soft mode, unless they're spin orbit coupling. So now I told you the story about how this was found. It was predicted. Okay, it was found, but then it's like a Cheshire cat's smile. The foundations for the prediction were completely needless to say, there have been a lot of theories since then. So I'm going to here refer to a wonderful recent review by my friends Maria, Jonathan, and Raphael. And let me just sort of summarize a little bit the main areas of the review. There's the extension of conventional BCS, as we just discussed, multi-valley approach. Okay, here the idea was to use large Q vectors, okay, to associate with the intervalley scattering to avoid Coulomb repulsion. People looked at plasmons, okay. And then Nagai in the 70s suggested that, look, we know that we need large momenta. What worked with Marvin Cohen? What worked was that we had large momenta. So actually Nagai, having talked to Jai Raman, who did Raman scattering and was interested in two phonon processes, Nagai actually suggested that maybe you may not be able to couple to one phonon, but you can couple to two phonons. Now here, the polarization is proportional to the displacement. So when I write this, this is the polarization squared. And here the idea is that I have the polarization squared coupled to the electron displacement. And we'll be talking much more about that here. But now more recently, and there are also dynamical aspects of this, which again, we're going to be talking about more recently, shortly. But in recent years, because of the interest in quantum criticality and the experiments, for example, of the Lonswich group and others, people have realized that quantum criticality is also important. So people have looked at the question in general of dilute quantum critical polar metals, not necessarily doped strontium titanate, but for example, what happens when you're near Dirac cones? Okay, can you get some interesting superconductivity, multiband effects? There's also been suggestion of spin orbit coupling. So the notion is that you can have this Rashba type coupling. If you have the Rashba type coupling, then you can have direct coupling to the critical mode. Okay. So one of the things we set out to do is, particularly related to strontium titanate, is in the disordered phase, you're going to have a dynamical Rashba coupling because you won't have a macroscopic polarization, you'll have a local polarization. And one question that Pavel and Abhishek, who's another postdoc at Rutgers, and I looked at was, can we come up with an experimental way of determining the size of the spin orbit coupling to see whether or not we really do have spin orbit coupling, okay? And what we realized is that if you have this dynamical Rashba effect, your electron fluid will have collective modes. And if you turn on a field, you'll get these spin flip modes, okay? That's well known. All right, but now if you are close to a polar quantum critical point, you'll also have a soft phonon, and at some point, you'll get an anti-crossing and hybridization. And normally with a polar material, you don't want to turn on a magnetic field, okay? But if we have this dynamical Rashba, we should actually have some hybridization. And it turns out that you can calculate this gap as a function of lambda here. Lambda, sorry, is G from before, the coupling. And from that, at reasonable fields, you can actually do an experiment to see how large this coupling is. The other thing you can do, which we're in the process of doing with our Rutgers colleagues, is DFT calculations for particular materials to see which couplings are larger. Okay, so those are in progress. So let me tell you the guiding observations that our Mary Gang, Pavel Pirzhai have had in our approach to this problem. First of all, we have strong ionic screening. So we have very weak interactions between the electrons. The dielectric constant is very, very large near a polar quantum critical point. Okay? Second is that the critical mode is inversion symmetry breaking. It's a transverse optical mode. There's no linear coupling to the charge density. And the assumption is that we have negligible spin orbit coupling. Remember, we're talking about the elements involved. In general, we wouldn't expect our low Z, we don't expect them to have large spin orbit coupling. Okay. All right, so we're going to ask, what happens if we don't have large spin orbit coupling? Is there a way to make this work? Now, the electrons do not interact directly with the 0-point fluctuations, right? And this situation is somewhat reminiscent. One of the things we love about physics is when different concepts show up in different places. This idea that the electrons do not directly interact with 0-point fluctuations is somewhat reminiscent. Is reminiscent of the situation. Oh, I've really gone over, sorry. But we had some problems at the beginning. Okay, so I need to speed up. So let me just tell you what we have. We have H, which is local density times proportional to the energy density. And we have a suppression of the 0-point fluctuations of the critical phonons near the electrons. And this leads to a reduction of the chemical potential of nearby electrons. And what we have is an attractive potential. So what's the action? The action looks like this. And we have electrostatic interactions and polar fluctuations. And for G equals 0, we completely decouple. Okay. So they're completely decoupled. So do we have weak versus strong coupling here? I want to get to the results, so I'm going through this quite quickly. I'll be happy to go over it with anyone. We have, because, let's go back, weak versus strong coupling. We are in the weak coupling limit. Even though we're dilute, because we have a large dielectric constant, it means we're in the weak coupling limit. That's very good for doing calculations. So we're in the weak coupling limit, which means we're allowed to do perturbation theory, okay? When we do perturbation theory on the energy fluctuations, the leading order diagram is a 2-phonon interaction, okay? So that's where we're going to do our calculations. In 3D, that's the same thing as energy fluctuations because the phonon-phonon interaction gives us a logarithmic term. In 2D, we have a different situation, okay? So it's in 2D that the energy fluctuations and 2-phonon are separate. One of the appeals of this is that 2-phonons have been very helpful in understanding transport. And the idea is to expand on this mechanism for superconductivity, but to include quantum criticality. So when we couple to the electron fluctuations, we find that a finite energy density, we can understand how we have a suppression of the polar state by charge doping. And this has been seen a long time ago by Jonah and Shirani. And this was not explained before. And we get it just automatically. And I draw your attention to the fact that the couplings that they get are, we're going to see that everything's consistent. So one of the appeals of this is that you can understand several experiments at the same time. So the key thing that you have to do is the energy fluctuation coupling can't be integrated out exactly, okay? You have to check that the Fermi liquid is stable, okay? Yes, it's stable. We can do perturbative effects, and what we get is our interaction that's relevant for the electron pairing when we average over everything, okay? It's dependent on large momenta, this is the cutoff, and it's dependent on 3 energy scales, each of which is density dependent. So let's just Fourier transform in real space and look at how this works. we have 3 different regions. We have the first region here at very low densities. Here we have omega T, 2 CSKF, and EF, all that are density dependent. The first one, we have no Q dependence, no omega dependence. At higher densities, we have no omega dependence. And here we have no Q dependence. I should say that there's a Russian paper which looks at the very low density limit. We didn't look at that because that tends to be filamentary. We focused on this. Okay, so we have no dynamics, but we have spatial dependence. And where this all comes from is at the critical point, we have basically a 1 over x to the 4th, and then we have to, that's good up to some cutoff, which will be density dependent, and that's where this comes. Okay, so what do we get? What we get is that we have an attractive part of the electron coupling. Here we have KF, which is coming from the density states. We have a log term. You see that when this is like a cutoff for the transverse optical mode, when the numerator is larger than the denominator, this goes up. When it's smaller, it'll come down. So we have a dome-shaped behavior with a maximum here. You notice that this here, I average the S, and the reason I average the S is because the dispersion goes like that. And so I want to average over the Brillouin zone because I'm using large wave vectors, okay? And so the maximum is actually away from half Philly. All right, and so this means that it's less than 1. I can then, the Coulomb interaction, if I include the Coulomb interaction, it's going to be just dependent on the density of states. So I'm a constant, so I'll have a minus sign times some constant. So at low densities, this will always win. At higher densities, of course, Coulomb will win. And I can plug into what Gorkov taught us about what to do in this situation. So I have a TZ that's a function of carrier density. So what happens when I apply it to strontium titanate? When I apply it to strontium titanate, these are the experimental. This is the second dome. These are the experimental points. This is what we get for this coupling of 0.68. Okay, if you take away Coulomb interaction, which is not strictly speaking legitimate, you get something like that, just to show you that you have a dome even without the Coulomb. And if you apply pressure close to the quantum critical point, you get this. And the key thing that we're proud of is the fact that the maximum seems to be about right. It doesn't have a G dependence. It's not dependent on that. The reason that we have this line is technically our results are only good up to here. Okay, when EF is less than this, above here, we have to include dynamical effects. Physically, we only took into account the ionic part of the dielectric constant, but as you go to higher density, you have to take into account the electronic part. We know that the Coulomb interaction increases with frequency. We know that this will decrease. So in this region, though we haven't worked it out, we expect that the interaction will have a change in sign as a function of frequency, and then you may be able to play with retardation. But strictly speaking, our results are not appropriate here. Okay, but in the very dilute limit, they're fine. All right, so this is what works with experiment. We connect with Harold Huang. We can connect with Gill's experiments. What's our prediction? We have a prediction in 2D. In 2D, the singularity will be more enhanced. Okay, if we take the interaction and do a Fourier transform in 2 dimensions, our singularity will be more enhanced. Okay, this is relevant for film. Now in 2D, I should say that's where energy fluctuations versus 2 phonon exchange are important. Shows up in the interaction. Okay, in 2D, we have the phonon-phonon interactions are very important. In fact, they stabilize the spin liquid, because if you just look at the scaling dimension, originally it looks like a Fermi liquid is marginal, but then the phonon-phonon interactions actually stabilize it, but they're very important, which means we have the absence of well-defined phonon quasi-particles, but energy fluctuations are well-defined. So that's where the distinction between energy fluctuations and 2 phonons are important. We've focused on low carrier density regime where the recoupling approach is okay, and it's a first step towards setting in. I'm almost done. What are the distinguishing features of what we've done? Well, I think, to me, what I like for the low density regime is that there are a number of measurements that come under the same umbrella. We have T squared, we showed the suppression of the polar state, and for all of these, the couplings that we put in are in the same ballpark. That's good news. So it's a unified approach to different properties. What are some things that we expect? We expect a scaling of TC with phonon frequency and sensitivity, carrier density at low doping concentrations. And I think one of the key features that distinguishes us from many others, particularly those with spin orbit coupling, is we expect a normal state near the polar quantum critical point that's a Fermi liquid. And so we don't expect unconventional superconductivity. We don't expect anisotropy. This is a superconductor that's coming out of the Fermi liquid. Okay, so thank you very much for listening, and sorry that I went over time.